everyone, welcome to today's Explainer. We're diving straight into an absolute marvel of modern mechanical engineering, the Synchronous-Strike Magnetic Separator, or, the SSMS for short. If you've ever geeked out over how machines transfer energy with absolute uncompromising perfection, you are in for a real treat. We're going to take a journey right through the precise kinematic chain of this device, tracing the flow of kinetic energy, literally microsecond by microsecond, to see how true industrial precision is actually achieved. Okay, let's quickly look at our roadmap for this. First up, the mechanical heart. Then we'll hit the TDC-actuated trigger, followed by releasing the magnetic weight, and finally, we'll wrap up with the kinetic toggle strike upgrade. Let's get into it. Section 1, the mechanical heart, setting the rhythm. Before we look at the hardware itself, we absolutely need to lock down one fundamental concept, top dead center, or TDC. Imagine you're pushing someone on a swing. TDC is that exact weightless fraction of a second where the swing hits its absolute maximum height, momentarily stops, and is just about to fall back down. In our machine, this exact geometric peak is the absolute linchpin for the timing of the entire mechanism. It all revolves around this single point. What's really fascinating here is the sheer dedication to eliminating friction right at the source. We've got this low-friction crankshaft rotating super smoothly, and it's fully supported by advanced silicon nitride ceramic ball bearings. These ceramic bearings are a huge deal because they ensure that as the offset timing cam starts its rotation, there is virtually zero energy loss to heat or resistance. This right here is where our entire mechanical sequence is born. Now, as that crankshaft turns, it converts that rotational energy into pure, unadulterated vertical thrust. The Neodymium Magnet Piston, the NMP, is driven upward, but it doesn't just flop around loosely, not at all. It's guided perfectly straight along precision linear rails. So the energy travels upward cleanly and aggressively, thrusting the magnet piston exactly toward its peak. Moving right along to Section 2, the TDC-actuated trigger, the critical microsecond. As the NMP travels up to the very top of its stroke, it approaches the MAM, that's the magnetic attractive metal interface, and there's this 1.5 millimeter critical breakaway gap. It's tiny, but as the magnet creeps closer and closer to that metal, the magnetic tension just completely skyrockets. The machine is essentially winding itself up, building into the state of extreme potential energy. So the really crucial takeaway here is that this entire mechanism operates on absolute zero tolerance. It's a perfectly choreographed high-wire act. If the system triggers even a fraction of a millimeter too early or too late, the magnetic separation completely fails. In this setup, timing isn't just important. Timing is absolutely everything. And that brings us to the exact split-second interaction that defines this machine. At the absolute mathematical peak of its stroke, exactly at top dead center, the rising neodymium magnet piston physically strikes what's called the lock-open switch of the MAM. It's a totally binary moment. The switch gets hit the exact microsecond the piston reaches its apex, and boom, that triggers the next phase of our kinematic chain. Section 3, releasing the magnetic weight, mechanical consequences. Inside the top assembly, there's this brilliantly simple bistable spring mechanism. Look, if you've ever sat in a meeting and endlessly clicked a retractable ballpoint pen, you already intuitively understand how this works. The moment that lock-open switch is hit, this click pen mechanism instantly changes states. It releases its hold and allows the entire system to physically transition. As the system unlocks, we can actually trace that mechanical release traveling back downward. We have this dedicated, highly rigid aluminum and carbon fiber link rod. This arm basically acts as the messenger. It takes the kinetic signal from that click pen release up at the top and firmly guides the path of motion downward to dictate exactly what the rest of the machine needs to do next. Which brings us to Section 4, the kinetic toggle strike upgrade, conceptual evolution. Let's see how all of this builds into an incredibly efficient delivery of power. Picture this invisible kinematic chain reaction based on the latest conceptual upgrades. Step 1. Once triggered, a heavy non-magnetic weight, the NMW, unclasps. Step 2. Instead of just a messy, wobbly freefall, this weight drops flawlessly down its own separate, dedicated ball bearing track. Step 3. At the very bottom of its fall, the weight strikes a specialized toggle joint. And finally, Step 4. That joint instantly redirects the downward force, thrusting a vertical rod perfectly straight up into what is known as the seesaw strike receiver. Now, to really appreciate how revolutionary that straight vertical thrust is, we kind of have to look back at the legacy system. The older setup was an arcuate strike force system. Basically, it used an arc mechanism, fulcrum, think of a seesaw pivot, to transfer the impact force in a sweeping, curved motion. Let's quickly contrast these two methods because the difference is a massive game changer. The old arcuate strike force relied on a curved, almost glancing energy transfer. And as you probably know, when things move in an arc, you inevitably bleed off kinetic energy into lateral forces. You lose power. But the new kinetic toggle strike system, it's pure, unadulterated vertical precision. By dropping that weight straight down on bearings and using a toggle to thrust perfectly straight up, virtually zero energy is lost. It is honestly a masterpiece of kinematic efficiency. When we step back and look at the entire SSMS, we're seeing a system where ceramic bearings, top-dead center actuation, and toggle strike kinematics all align just flawlessly. It really makes you wonder, if a single microsecond of synchronization can completely redefine the efficiency of this one machine, what other mechanical limits out there are just waiting to be broken by perfect timing? Thanks so much for hanging out with me for this explainer. Keep analyzing, keep learning, and I'll catch you next time.